Yeah, so we have started recording. Let me share my screen. Where is the thing? Oh, why does this thing disappear? I don't understand. A minute. Hmm. Okay, so since can you see my screen?
Yes, sir.
Yeah. So our norm has been always to go back to the problem, which is like, a definitive thing before we start any new topic. So here we are in our general scheme of trapping a nanoparticle. This is a schematic. So we have covered, the last thing we covered was how these things, objects which are uh, polarization modifying. So these are like birefringent or birefringent material, which are basically made out of optically anisotropic media. This half-wave plate, this is a polarizing beam splitter. So these things actually influence the polarization of a light beam. And the last topic that we covered was essentially looking at how these materials are made and also how you understand the evolution of polarization of light after they interact with such materials. What we do now is these lenses, mirrors, all this. How, and also very interestingly, this object, a laser. So one of the most important constituents of a laser, without which a laser cannot work, is a resonant cavity. So how does a resonant cavity work? What is the mathematics behind designing a cavity that will work? What is the meaning of the fact that a cavity will be, a cavity which is nothing but a fabric or interferometer, which is typically two mirrors, partially transmitting mirrors, which are facing each other. What is the meaning of, just these two mirrors being transformed into a resonator? Because a resonator is very powerful. Just putting two mirrors in front of each other might not actually achieve anything. So what is the mathematical description? How will you understand what are the rules that are need to be followed in order to transform just two mirrors facing each other into a resonator that is actually a very, very powerful instrument, which is the one of the, basically the reason behind which you observe lasing. Because remember, a laser, it stands for light amplification by stimulated emission of radiation. So that amplification part only happens because of the presence of a resonator. So we are going to learn all that in this topic that we are starting today. After this, of course, we go to the last topic before we actually look at maybe how traps work. Actually, how traps work will be covered by I think one group at least in the term paper. So I don't know, if we have time, we can either do that, do a bit of that in class, or maybe we can just get it, get the stuff from your friends. But at present, of course, the topic that we start today is sorry, interaction of light with optical devices, mirrors, and lenses predominantly, and resonators, optical resonators. Very, very important. Okay, so the book that is very good in this is is a textbook called Laser Optics by Miloni and Eberly. I don't. Well, okay, 1 minute. I don't remember if it is. Yeah, okay. There is no E. Possibly there is no E in the Eberly. Let me just check once. Yeah, there is no E. This is chapter 7 of that. Okay. So when I say so of course what we are trying to tell you is, suppose you have a light beam. So mirrors are a bit trivial, because when you have a light beam coming like that, a mirror will just sort of bend it depending on the angle of incidence. As long as the law of reflection is valid, that is fine. A lens is but of course a spherical mirror is much more interesting and much more complicated, right? A spherical mirror might have things like, if along its optic axis may actually focus it here, or depending on where the object is, it can actually put your light. I mean, the image may be formed, either it may be a real image, it may be a virtual image, all kinds of things. A lens is also pretty interesting. If you have a convex lens, you have something that is focused here along the optic axis, and again, depending on where your image is or the object is, the image will be formed in different directions. You can have real images as well as virtual images. Even for mirrors, you can have mirrors that are sort of stable mirrors, in the sense of forming nice good images, which are less distorted images, which are these concave mirrors. You can also have things like convex mirrors, where the light reflects here and then goes all over the place. So so what we will learn is how you will understand, like, how these objects will behave when light interacts with them, and where so basically a quantified description of what happens when you have light incident upon these. There are some measurements we're going to talk about, with key measurements which tell you how to trace. So essentially this is tracing a ray of light. So this is entirely geometrical optics. We forget about a wave here. We do not think about polarization, nothing of that sort. We basically trace rays. So there are some very powerful programs as well which achieve this. One is called Zemax. Zemax is a very powerful program which actually allows people. There's a lot of commercial interest here, by the way. A lot of industries there which help. For example, building headlights of cars and all. It's a real art. I mean, it's a whole scale of industrial effort which is actually put behind this. So Zemax is a very well-known software. There's one more software called ASAP. That is a there's, it is this is an acronym. I don't remember the full form, but Zemax probably also is an acronym. I don't remember again. This is probably the name of a brand or a company. So these are very solid, softwares which actually help you in ray tracing. And ray tracing is important because when you have, for example, just like something like a microscope objective lens. Do you have any idea how complex it is? So any microscope objective lens, it actually has inside it something like 15 to 16 lens, small thin lenses inside. So it is a very, very complicated object. And if you want to understand how such a thing works, it is best to these softwares actually help you design those kind of very, very complicated lenses, and arrangements of mirrors and lenses. For example, making a telescope is very, very complicated, and you need software. So what we're going to tell you is what is the basic algorithm behind which these work. Okay. And so this is essentially how light interacts with lenses and mirrors. The other part that is much more complex is resonators. So that I will actually show you some pictures. Yeah. So basically, what we have here is types of resonators, and as you see, this one is good. What is the meaning of a stable resonator and an unstable resonator? What do we mean by that? Right? This is what I want to tell you, and this is where it all really boils down to. So a stable resonator essentially means something where if I come in with a beam from this side, say, oh, this is quite bad. something like this, it will actually keep on. Oh man, I'm just not being able to continue this. Fantastic. Let me just catch this line. Yes. So if you have an input beam like this, these are two mirrors, of course. My the basic aim has to be to keep these rays go back and forth. Very if this doesn't happen, if you have this ray going out, then this is no longer. So this is a resonator. This is not a resonator. This is an unstable resonator. This is also a very stable resonator. So can you design this? What does it take to design resonators which will confine, a beam? Okay, a beam we will actually come to later when we discuss a Gaussian beam. But say rays of light, what allows you to keep rays of light entrapped inside two mirrors in such a way that they will keep on propagating ad infinitum inside that, inside these, this thing is basically called a resonator or a cavity inside the resonator. That is, what is it? What are the rules? There are rules, and believe me, it is not very simple to design resonator of such sort. So for example, there are many different laser resonators. This is a very simple resonator, but there are also resonators called, like, ring resonators, and I will give you an assignment on this. So these are also found in like many cavities, which actually look like, so you have an input beam coming like that, and you have as many as four different mirrors. So you have a beam coming like this, it goes here, it goes here, it goes here, and then it goes there, like that, and then it comes out through this. These are plane mirrors, these are convex mirrors. You have resonators like this. So these are very complex, but these are also very useful in certain applications. And designing these are extremely non-trivial. Okay, so this is the basic aim of what we are trying to, uh, 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 we were going to discuss for the next few days. So essentially, what we are saying is that stability conditions for resonators can be found quantitatively. And this is the whole thing that we are going to learn in the next few classes. Okay, right. So how do you find that? So obviously we have to define certain parameters in order to understand this whole business, in order to quantify how a ray propagates. Okay. So the first assumption, so basically, so what we are doing here is can actually be called studying the propagation of rays. This is this is the motivation. We are actually trying to find out, we are we are completely saying that light propagation here is only in the form of rays. What is a ray? That is the first question. That is the first question that will come to you. And again, I will use the advantage of whiteboard to oh man, you cannot edit this, is it? Okay, so we have to go out and then edit. So basically, what we are saying is so essentially, this is my wavefront. Okay, of if I consider, uh, these are essentially wave fronts. Okay, now my wave is traveling in this manner, right? I have a series of wavelets going like that, waves traveling in this direction. These are all wave fronts. What I am defining as rays is the normal to one sort of point on the wavefront. These are my rays. Okay, so rays I define as,
So why are we using different definition for rays? Like, it's not general in the sense that in the anisotropic media, we
hmm,
studied that this ray is
hmm.
essentially the in the direction of S vector.
It is the, yeah. So basically, in the yes, no. See here, what we are saying, yeah, in the sense that, see, this whole thing here, again, Hitesh, we are not really concerned about
Because
energy
here,
propagation or something at all. What I am trying to say is trying to sort of, we are trying to make an equivalence, or we are trying to make some common ground between a wavefront and what we understand as rays. So do not think of any energy propagation happening here. We are kind of saying that, so suppose you have a wave, right? So how do you reconcile a wave with a ray? Just think in terms of the geometry. The whole concern here is in terms of the geometry. Okay, so in the sense that if a wave I think as something like that, then it's difficult to say, associate a ray with this. So what I'm trying to say is, if I have a packet of waves, or a lot of groups of waves where I can define a wavefront, then a ray is something which is a normal to a wavefront at different points.
yeah, that is the
Okay.
direction of K itself. Like, yeah,
Yeah, basically that. Okay. So what I'm saying is, this is just each point, each point on a wave drawn like perpendicular to the wavefront, something that is normal. This is, again, I mean, see, these are, finally, when we are going to study how these are propagating, we don't really care about these definitions. We essentially consider that light is coming in the form of rays. We do not consider wave formulations here at all. Okay, there is no concept, very importantly, there is no concept of polarization here. We are not thinking about fields at all. We are only and only concerned about directions of the ray. Okay. And of course, this whole treatment can also be extended towards Gaussian beams. That is, we are going to study that, and it's not too difficult. But the basic thing is studying this, the starting point is to consider light as rays. And what I'm trying to do here is to reconcile the concept of rays with the, what we have been doing till now, that is waves. I do not think of any sort of parallels with energy transfer and all that, nothing of that. So this is just try to find out. So for example, here a crystal or something would be just a refractive index medium of something, of an object which has refractive index something, and that will bend the ray. That is the only thing that we care about. If it's a complicated medium, then of course it becomes different. If you have n as a function of z and all, uh, in that case, yeah, I mean, that case it becomes much more complicated. In fact, I am not, well, if you have n as a function of z, I cannot tell you offhand whether this treatment will work. But typically, we just consider constant refractive indices, just free space, and have constant refractive index. This is what we typically just think. Okay, and we, of course, we do kind of loosely say that, the, see, that definition that we had in the anisotropic media, this thing, that the direction of a ray is, that is not compromised, you can say, is the direction of energy transport. That is sort of, it's not really crucial here, but this is something which is not violated, that I can tell you.
yes, this is
And
definitely. The only point was that was more general
Yeah,
definition.
yeah, yeah,
So
yeah. See, only thing that I'm telling you this is that basically we are concerned with the direction. How do I reconcile? I'm just saying, yeah, you can say that. I mean, I can actually drop this definition and just say that direction of energy transport is the ray.
yes, because in homogeneous media that
Yeah,
becomes
yeah,
the
that
direction
is
of
the perfect. But yeah, but typically, yeah, you're right. So this thing is basically what I'm trying to say is this is like the k vector, right? So the k vector is a problematic thing, and I'm saying that as the ray, I am tacitly assuming that this is a isotropic medium. That I agree. I completely
yes,
agree. I am tacitly assuming that this is an isotropic medium. Totally agreed. An isotropic medium, it will be much more complicated. There we cannot have this. So I agree with this. Let me write this down. Valid for isotropic medium. However, the crucial thing that I'm going to write here is no consideration of polarization. Very crucial. Okay, now let us try to. Uh,
Sir, I
yeah,
have a question.
yeah,
Sir,
yeah.
in some cases, k vector and s vector can be oppositely directed. In that case, should we take the direction of s vector as the direction of the ray
A K vector,
instead?
S vector, mana you are saying, yeah, yeah. I mean, in the sense for anisotropic medium, there is a problem. This is not, I'm not even thinking of that. We are
Sir,
basically,
even in
uh,
isotropic media, I think that is possible in certain scenarios, right?
like where?
For example, if you have negative refractive index
Arey Baap re. Again, that is
in
also very complicated. See, this is not valid for things which are even slightly, yeah, I mean, all that metamaterials and all, they have some, as I said, so let us just write down the ray matrix. I sorry, okay, I spilled the beans out. Let us write it down. Then I will all that. See, any kind of, some kind of interesting things that you might have with refractive index, those we don't really, I don't, yeah, those become very complicated. Whether you can actually have this treatment valid for, you know, any complex refractive index property medium, that may be an issue. But if it's an isotropic medium, yeah, you can say that typically this is very crucial. This is the first hand definition. Okay, whether this will, as I said, this is valid for isotropic medium, but whether this is for negative refractive index, that is very complicated. I
because they
would
are also
probably. Mm.
isotropic.
Yeah, yeah, I agree. I agree. You're basically going to some energy where the n becomes negative and all. So let me.
Not only isotropic medium have to be linear to follow.
Yeah, 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 yeah. That is a very good point, actually.
Okay, okay.
That is a very good point. Very good point. So that covers this, what you're saying. So any kind of linear medium will not have that property, right? So this is basically in that linear region of this thing. I think that's a very good point, Bishali. Thanks for that. Okay, so now let us, acha, another very crucial assumption is that let us actually write down these are, I've written these extremely, let me just write this properly in terms of this thing. Yeah, the first thing is, as I wrote here, no consideration of polarization. And secondly, very importantly, rays propagate parallel to z-axis. This is also very, very crucial. We are the angle from the z-axis that we consider the ray to deviate, that is actually considered very small, where we, so that approximation of sine theta and tan theta equal to theta is completely crucial here. Okay, so there are things where, when you have that, and that is where again this whole thing collapses when you have tight focusing, or when you have lenses which have very short focal length. When this assumption is violated, actually this whole treatment falls apart. Very crucial. Okay, so almost collinear, not tight focusing. This is very important. This does not hold when you have, again, these things are related. When you have a strong Z component, that means very tight focusing. You do not, this whole thing will collapse. You cannot assume this way of propagation. Okay, so now what are we really talking about? So let me again use nice figures. 1 minute. Just give me a second. I'm going to use these. Yeah. Actually, okay, forget it. This one I don't need to try. I can just draw this directly. Okay, let me just go this down. So what we assume here are two things. So if this is my z-axis, this is my propagation direction, z-axis, I have, say, a ray starting from here and traversing in this direction. Okay. Then I assume that this is theta. This is my ray traveling in that direction. I measure two things. One is the deviation or the displacement from the Z, which I say, for example, here this is Z1, this is R of Z1, and say this is Z2. I say this is R of Z2. So two measurables, there are essentially two measurables. One is the transverse displacement RZ, and the other is the slope R dash Z or dr dz. Essentially, these are the two things which tell me everything about the ray in the treatment that we are going to follow. Okay, the displacement of the ray from the z-axis, which is this one r1, the rz1, rz2, and the angle that it makes. That is what we trace when we try to find out how a ray interacts with an optical medium, with a lens or a mirror or something like that. Okay, so very clearly what you have here, let me just, I think we should just, can I just copy this part? Is this copy? Oh shit, there's no copy yet. Copies. Only copied partially. It's okay. So quantifying the propagation of a ray. Right. So what we wrote down was this one was R of Z, Z1, that is Z2. So this is Z1, this is R of Z2, right? Okay. So essentially your R dashed or dr dz is nothing but R of Z2 minus R at Z1 by Z2 minus Z1, right? Which means that my R of Z2 can be written as R dash into Z2 minus Z1 plus R of Z1, right?
Sir, this Z direction is defined with respect to what?
So this is basically when we are going to do the optics, optic, when we typically will look at different optics and all, this is the will be the axis of the of whatever we take. So this is like, when we suppose we take a mirror, say a lens, sorry, a lens, say this this is your Z. Okay, this is some kind of a axis. This is some kind of an axis which passes to the center of your optical device, something like that. You measure, this is like, for the lens, this is like a principal axis. For a mirror or lens, this is like, yeah, whatever. And you measure the displacement with respect to this line that passes through the some kind, so some axis of your whatever optics you are using, basically that. Okay.
Okay, sir.
Okay. So another very crucial assumption is that the theta is very small, extremely important, so that your r dash is essentially tan theta equal to, oh sorry, this is almost equal to tan theta almost equal to sine theta. So essentially what we are considering are paraxial rays. Very, very, very important. This whole thing is under the paraxial approximation. Okay, so however, this is the crucial thing, is that this is how a ray propagates. So I can, this at this moment in vacuum, for example, this Z is arbitrary. This is with some kind of position, some lab frame that I define, with respect to which I measure the transverse displacement of the X. Typically, this Z, this axis becomes important only when I have an optical device, when I have propagation through free space or vacuum. So the axis with respect to which R and R dash are measured may be arbitrary in free space, but are typically the principal axes of lenses or mirrors. Okay, so then this is basically what you're going to have for in vacuum. Now, and that is the crucial thing. So you can also very clearly see that so this is how RZ2 and RZ1 are related. So very clearly R dash of Z1 is the same as R dash at Z2, right? Because these are the same angle. This is just, if this is, I'm measuring with respect to the same axis. Very clearly, these are parallel corresponding angles, right? And now comes the important way of describing this. Basically, I will write this in a matrix representation. RZ2, R dash Z2 can be written in this form. RZ1, R dashed Z1. And this, friends, is what is called the ABCD matrix. ABCD means this is A, this is B. So what we finally have is, if you really write it in forms of an equation, what you will have is RF, RF dash, A, B, C, D, RI, RI dashed. So F means final, I is initial. This is very, very important. This is basically this ABCD matrix or ray matrix is a universal treatment for any kind of ray propagation. Any kind of ray propagation. So if you have whatever complex, a kind of material that you have light coming through, as long as it is paraxial, that is tremendously crucial. If you have paraxial light propagating, this is valid. This whole thing can be, this is just beautiful. This will really tell you how a ray will traverse, along, traverse as it interacts with different kind of optical devices. Extremely important. So let me nicely mark this in red.
Sir, if you have two different media,
Yes.
then your this second equation, which is r prime at z1, won't be
Mhm.
equal to r prime at z2, right?
So different media, basically, Hitesh, we will act on this on, like, you will, each media is treated with a different ABCD matrix, and just as you have for different polarization components, you will keep on putting ABCD matrices from the left. So the first one in interacts will be first, then you have something on the left of it on the same thing, then it continues like this. If it is very importantly, if you have refractive index of n, for refractive index of n, you basically have your ABCD becomes 1 Z2 minus Z1 divided by n 0, 1. And this is something that I will ask you to prove. Anything that you have, the refractive index, basically the general formula is Z2 minus Z1 divided by n. Okay. And if for a mirror, however, there is not, so yeah, so basically it is just this. I mean, there's not going to be any change. Okay, so if you have just traversing in free space, it is essentially just the final minus initial coordinate. There's no other change. What becomes interesting is when you have different optical elements, and that's what we are going to consider now. In the sense, we are going to look at how mirrors and lenses behave. So the first thing that we are going to consider is a thin lens. So the whole thing, we are, how we, when you have different optical elements, we are going to show you how it works. I'm going to actually make you work them out, and you can see how they will work. So the first thing we're going to look at is a thin lens. 1 minute. Just give me a second. Just give me 2 seconds here. This is my thin lens. Okay, this is my thin lens. Okay, so as you see, typically we measure with respect to this axis which goes to the center of the lens. Okay, and acha, now come the very crucial conditions. Okay, so basically this is your, yeah, as this is direction, this is there, this is this. So acha, some convention, again very important convention, is that, so Ri dashed is again, of course, so yeah, so one very critical assumption is that, so if I draw this axis here, right, so the displacement is basically from with respect to this is Ri. So at this junction, okay, so Ri is here, Rf is there, so basically Ri is equal to Rf. exactly at this. Okay, very, very important. Right on the interface, on the exactly at the interface, Ri and Rf have to be equal. Exactly like at infinitesimal small distances away from the interface, Ri is equal to Rf. Very crucial. Second assumption, very important again. I consider Ri dash to be positive and Rf dash to be negative. And don't jump at this, I'll tell you why. Because the convention is that the gradient is positive or negative depending on whether the axial displacement is increasing or decreasing. Is that clear? Very important. Again, I repeat, the gradient is considered positive or negative if the as per whether the axial displacement is increasing or decreasing. So very clearly, so the gradient is considered positive or negative depending on whether r or the transverse displacement is increasing or decreasing. Extremely important. Oh shit, decreasing. Okay, so very clearly you can see here the gradient is increasing. I mean the displacement is increasing, here is decreasing. So Ri is positive and Rf is negative. Rf dashed is negative. Okay, very nice. Okay, is this clear? This is very important. This is a convention that is absolutely stuck to. Okay, so we have, it is obviously that Ri dashed is Ri by do and Rf dashed is, because Ri is equal to Rf, it is minus Ri by di, right? And we have also the Lensmaker's equation, that is 1 by 1 plus do plus 1 by di over r and I are of course object and image distances is equal to 1 by f, right? So very, very easy. Then we will, so essentially I again want to create that kind of ray matrix. Okay, so I will try to basically get rid of one of these. So something I have to get rid of, right? So I have, so from here I have 1 by di is 1 by f minus 1 by do, which basically means that my minus Ri by di is Ri by just 1 by, so this is minus, so 1 by do minus 1 by f, right? So that means my Rf dash is Ri dashed, Ri by do is Ri dashed, right? Ri by do is Ri dash. Ri dash minus Ri by f. Clear? Very simple steps, right? So that means I can compose my matrix because Ri is equal to Rf. I can basically write down that Rf, Rf dashed is 1 0 minus 1 by f 1 Ri dashed. Clear? Is this fine? Very, very simple derivation, right? Ri by this is Ri dash, and you can just see that Rf is very clear. Achha, this is Ri dashed. Okay, very, very crucial. Any thin lens, how the rays kind of go, if you want to design a certain lens system, then this is just, absolutely the how a lens will basically transfer the ray from the object side to the image side. Okay, so after this we will try, which is a bit more complicated, is the curved mirror, which is somewhat similar to a lens, but I basically am showing you how you kind of do these. Okay, so we can look at a curved mirror of curvature R. So this is again concave convex का एक positive है एक negative होता है, so that is again complicated, so we will just come to that. But this one is lightly थोड़ा सा ये है, but it's okay, it's just simple geometry, most of it. Okay, so let me just get this. Okay, this is what's happening. I am getting my ray coming from this direction. This is my ray. ऐसा जाके this is essentially coming here. So see, one very important thing, I am not assuming this from, and this is arbitrary, this can start from anywhere. Okay, this is just going from anywhere. Okay, so I'm not assuming whether it's before focus, after focus, nothing, this is just going anywhere. Okay, so this is coming here, from here is reflected out here. So this is basically my normal, and yeah, so this is essentially this, so this normal is this is basically my normal, and of course the ray is reflected here. Okay, this coming here, this is how do I get the normal? I draw a tangent and I draw this thing perpendicular and I extrapolate it here. This is the angle it makes with this is beta with respect to this. The normal of course is with this thing, and the ray is it comes here, and the resultant, it is sort of, you know, the mirror sort of focusing is a bit of a loose word, but it directs it here, where the axial angle is now gamma. So this is much more complicated than
So we are taking small arc, right? Like the mirror is a tiny arc.
yeah, the radius
that
of
approximation of that focal point can
yeah. So of course that I am in the sense that this curvature is it is not too much actually. It is
like a
not
small angle basically.
right. All of these are very small angles. That is, all these are badly exaggerated. Okay, these are all badly exaggerated. So once again, you have your Ri equal to Rl, and this is quite obvious because obviously it's coming in the same side, so it has to be the same. Okay, and now, however, there are some important things. So the basically this gamma. So this is basically your object, and essentially this is your image. The ray is focused here. I mean, so it's directed by the mirror here. Okay. Now, basically, you have to remember that famous law of triangles, that your exterior angle is sum of interior opposite angles, right? That is very important. And if you remember that, then you can straight see that your beta is alpha plus theta, right? And your gamma is straight beta plus theta, right? This is this plus that, and this is this plus this, right? Which means that gamma is basically alpha plus 2 theta, right? Acha. And also you can get that alpha plus gamma. Why am I doing this? Because again remember, my motivation is to get your RF dash in terms of RI dash and RI. Only that. I have to get that matrix thing right. So I have to get your RF dash in terms of RI dash and RI. Okay. So alpha plus gamma is essentially, because see, remember my RF dash is essentially tan gamma, and your RI dash is tan alpha, right? So somehow I have to get that gamma thing here, right? So anyway, so alpha plus gamma is like 2 beta, and that 2 beta, so acha, this is another small thing that we are actually going to say, that this beta, tan beta is Ri by R. That is this again. This is again, I am sort of assuming. Okay, this we have to assume. This R is a bit, this is actually slightly off, but of course tan beta equal to beta, but this is again approximate. This is by R. I'm assuming this distance we are sort of ignoring. Okay, and you know that your RF dash is tan gamma, which is again equal to gamma. And now this part is clear, right? So remember, we are trying to get gamma out. That is what we are trying to get. Now another very crucial convention, that is the radius of curvature r, we consider that to be positive if rf dashed is negative. Repeat, the radius of curvature r, that is for concave mirrors, we consider that to be positive if your rf dashed is negative. Rf dash is negative here, right? Because the displacement is reducing as the ray propagates. The transverse displacement is going down. Okay, so convention for curved mirrors is that if rf dash is negative, r is positive. So convex mirrors, you can appreciate that convex mirrors, you can appreciate that this will come like this and it will go like that, right? So the rf dash is going to increase, so that these are the r is negative. Okay, so then from here we know that we basically can say that rf dash is minus of gamma, right? And minus of gamma mane is alpha minus 2 beta from here, right? Minus of gamma mane, gamma is 2 beta minus alpha, and minus gamma is alpha minus 2 beta, right? And of course here tan alpha is basically alpha equal to ri dashed, and that implies basically rf dash is ri dash, and beta we wrote this to ri by r. Fantastic, right? So straight from here we can write that rf prime is 1 0 minus 2 by r 1 ri prime, right? So so as I said, concave mirrors r is positive and convex mirrors r is negative. Okay, by the way, so can you see that so remember for lens, what did we have? So if I can write down the terms of focal length, what will this become? What will this become?
Minus 1 by f.
Exactly, and this is exactly what you have for a lens. So essentially this remains the same. Exactly. So in effect, a concave mirror and a convex lens behave in a similar way in treating the ray. Only, of course, the direction of the ray is sort of, yeah, but that you have to keep in mind, because one will transmit it and the other will reflect it. But the behavior
Sir,
is exactly the same. Huh. Anirudh.
what exactly is r dash? As in, is it dr by dz?
Yes.
Be- Because in the
Yes.
reflected ray, it's still. I mean, it's the slope of the line is still positive, right?
Yeah, I
Like, what is
completely
the rigorous
agree.
definition? Like, why is it
Yeah.
negative?
It is dr by no. That is just, see, because I have to differentiate between the see, because I see we are trying to say okay. So rigorous definition is completely dr by dz, but this dashed rf minus thing, this minus sign essentially tells you the direction of reflection. Okay, so if I say that this is negative, then you know that the ray has to go. So basically, for example, think of a concave lens, concave lens. Sorry, then it will always come like that. This will come like that. But for a convex lens, it will go like that. And so
Yeah,
whether
yeah.
it will
Like,
go by this way,
physically,
so
I
that is
understood, and
that
even
is the only
I
thing I'm
understood
doing.
what the negative implies. But I'm
Right.
just saying, ki, how would
I
you
am putting it from
rigorously
outside. Anirudh,
define
I'm putting it
RG?
from outside. I'm putting it from outside. I don't have, I can't really defend this, that, I mean, just I'm putting it from outside. I'm just
Okay.
saying that this is minus gamma because I want to differentiate from, and this is like how you put spin in the Schrodinger equation. I'm putting it from outside. I'm not saying that the rigorous definition is just d at dz. And this continues to be like that. I don't see, I'm saying that if it is going Yeah, so basically my convention is that if it is the thing goes, the transverse displacement
Sir,
reduces,
I think
I say
we
it's
can
negative.
rigorously define it by, instead of saying dr dz, we can say
Hmm.
dr, as in instead of z being the path, as in we can say z could be in the direction of the ray path, right?
That way. No, Z being the direction of the ray is a problem, no? Because we are measuring with respect to this thing, no? So, Z vector, you can basically say this is something like that. This. This you say that might make sense. If this is going this way, then I'm saying this is negative. Or that also, yeah, something like that. Rate of change. I mean, if it is reducing in the sense
Sir,
that
maybe if you include time into this, then
बाप रे.
can, like, time derivative can give you something negative.
Yeah,
Like the z
I
component का time
know. Yeah,
derivative
yeah,
will
yeah,
give
yeah,
negative.
yeah, yeah, yeah. Okay. Okay. So that is an interesting thing. Nobody has. Uh, yeah, I'm saying that. Yeah. So well. Yeah, that may be an interesting thing to say. So if we can say that R of T1 is less than R of T2, then we say that R dash is negative. Something like that.
Yeah.
Yeah, that we can say. Okay, yeah. If you say that dr dt is negative, then this becomes. But that is something which we keep aside. In the sense that we keep that in the back of our mind. So if you want to draw a ray tracing picture, which is what is important, then you just this definition is
But
fine.
I
If you
think if
just
you
know that.
define
Hmm.
dr dt as r dash, I think it will work, I think.
Nah, but then how do you say how the alpha and beta and gamma? How do you say that, right? Because when I try to construct the ray matrix, then I have to say that this tan gamma is gamma and gamma is given by this and all that I have to say, right? This step that I wrote, that beta is 2r by r, right?
Okay,
That
sir. Let's move on for now. I'll just think about
we
it.
think of a thing, then we can try to. Then this
Yeah.
will be a new Anirudh algorithm, new thing. But
Sir,
this is nice. It's a good thought.
z at fixed
Ah,
z, isn't r of t a constant?
at fixed Z, yes, of course. At fixed Z,
Yeah, so what does r of t means?
Okay,
yeah,
so like what I meant was
CD
kind of like
matrix is
instead of
no. So,
instead of
so,
a
so, so wait,
continuous ray
guys,
of
As T increases, Z also changes. That's what I'm saying. So as
uh,
T increases, Z also changes.
sir,
What I'm
what
Yes,
saying.
it's a
Hitesh
function
meant
of your
was
z.
if you have a ray, the
Uh,
No,
ray does
then
not
it's
change with
z
time. It's
itself. No, wait.
no, I'm
It's
saying that as time goes, then Z progresses. The ray progresses along Z. So we are saying that as T increases, Z changes. Whether it increases or decreases, yeah, Z changes. That's probably the best thing to say. It progresses. So it, yeah, this, for example, here it does not increase, so Z
There,
changes is what I'm
as I
saying.
know,
z
sir, that
is
this
independent.
positive and negative thing depend on the image position. That's why
Ha,
this thing,
ha.
this is just a convention. And
Mm.
what T does not, because this is the characteristics of the that optical element that
Ha.
has to be
Yeah, but
depend on
then
only theta
Vishwajit,
and
we can take it out of that. We can sort of make it sort of a general thing by the definition that if you have R, the R decreasing for the image thing, then it is negative. That is the
so
same thing as
no,
forming on the
actually
other
not
side of
that
the
sense.
lens.
Actually, as I know that if the image means if the ray is
But that is
propagating,
all the same thing, na?
yes,
When you are saying that is also going to account for the exactly same thing, right? If you have the
but
image
these
on the
things are
other side, then it's going to increase, right?
these
If you
things are
have
really means
just as
that
you
T
have
thing.
for
I am not sure.
no. But this is if you look at textbooks, then this is exactly what they have said.
sir,
This is
I don't
exactly what
think
they
you
I can
can.
understand your thing is correct. I'm
ha,
not
ha, ha,
saying about it,
ha,
but
ha.
this thing that T thing that
T
incorporating
thing,
time element,
no.
yeah,
T
that
thing
thing.
is something which we wrote because Anirudh wants a absolutely general thing without any definition, whether it can follow. That is an
Sir,
interesting statement. Bolo.
one thing I can observe from here is that you can't uniquely identify a ray, as you said before. Like, consider the
Hmm.
diagram. you've
Yeah.
drawn a ray at an angle alpha, that is the
Right.
initial ray, right?
Right. Right.
So
Right.
instead, if it was minus alpha, that
Hmm.
would have an r dash as negative.
Uh, and this coming from here.
Yeah. So that will also have an r dash as negative, and compare that with the other ray. Both those rays have can have, like, consider uh,
Yeah, but that also is
having the
like
same
decreasing,
amount of
right?
r dash, but
Yeah,
they
yeah,
are
but that
propagating
that
in
all.
different directions and have different
Yeah, but
geometry
there
around it.
also, your magnitude of R is still decreasing, right? So essentially, what we want to say is that the magnitude of R, not so. I don't take that this is positive and that is negative.
So
Even
it's
if
the
we have
slope
minus
remains
alpha,
the same. It doesn't contain, like, even if you change the direction,
it
invert
will
the
still be the
direction,
same.
yeah, it will
It will
still be
still be the
positive. It
same.
won't be,
It will
it
still
won't
be
become
positive.
negative
Exactly, it will
because
not become
slope
negative.
doesn't have a direction.
Yes, it does not have a direction, right? So it will still be
Also,
negative
sir,
or positive.
you wrote as t increases, z changes, but z is an independent variable.
Yeah, I'm assuming. See, this T thing we never ever think of putting in ray matrix. Okay, it is just because what if we can say that as time goes, the ray is progressing. It's not fixed at a point. That's what I'm trying to say.
So, like,
As
what my
time
only
changes,
point
the
was
ray
that.
progresses along the z. Along the it is ray money. It is progressing with time. Okay, but
So
RT1
consider
is
There is
this.
a
different
wave
from
of,
RT2.
So
I
consider
mean,
this vector alpha beta. Like, just draw alpha beta. I mean, you can draw two possible rays that satisfy same vector. Like, you won't get a unique vector. It could either be at an angle alpha, like you've shown in the diagram, or it could
Mhm.
be the same ray propagating in the opposite direction.
Same way, opposite direction, but this direction, this way. Yes, yes, yeah, but then the object will still be there, no? If this ray is going that way, and if the mirror there, then the whole thing still holds because I'm still going to have the R dash will be still positive.
Yeah, basically, I
Huh.
just meant that a particular vector doesn't uniquely define the ray. Like,
No,
there's
no, no,
still.
no. It does not differ. No, 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 no. In the sense that, see, I can always change my origin or something, right? Or my where I'm measuring it with respect to that, I can keep on changing, right? I mean, that can change. I mean, so I mean, what this alpha is completely arbitrary, right? I can choose in any direction, any way, whatever. But still, the magnitude of the transverse displacement decreasing, that we are sticking to be as negative sign for the gradient. That I think is a consistent definition. Okay, and I am just saying that as time changes, as time evolves, if T1 is greater than T2, then the magnitude is, if the magnitude I'm saying of R reduces, then we say that R dash is sort of, so if I say that this,
So that's what my point was. Like, time
hmm,
prescription is required to make it consistent.
yeah, I mean, consistent, but I can always define that also, right? I mean, this is a definition that comes, which is also consistent. I mean, you could say that if the magnitude reduces in time with respect to my measurement axis, which is consistent, that measurement axis has to be the same, right? I cannot arbitrarily change that. Then it doesn't make any sense. With respect to whatever when a longitudinal direction I was measuring, if the magnitude is reducing, then I say that this is negative, that the gradient is, the sign is negative.
so can you write one functional form of r of t?
No, baapre.
I
I
mean,
mean, it's a straight line
doesn't make
typically.
sense. I mean,
It doesn't make
how
sense.
can you represent r of t?
I'm saying that, yeah, well, if so no, but here we are saying that these are straight lines. I'm not assuming any curve. I'm assuming these are all straight lines.
That is in wave optics when we write the equation that of the,
No,
like,
no,
I
but
will
hey, Hitesh, these are all valid in that, man.
no,
These are
but then
all valid in wave
how would you
optics.
represent r of t? That's my question.
So the main problem I think he has is, here we are considering a infinite ray kind of thing. Like,
Ha,
there is
ha,
no
ha.
position of the ray. But when I said RFT, I meant that like, kind of like Newton's corpuscular theory, where light is stream
So
of particles.
it's like a wave with zero
It's
amplitude.
yeah. I mean, in the sense that this is a very vague concept. Yeah, yeah, I agree. I mean, you can, but this is okay again with I am measuring with respect to a fixed axis. If I am saying my measurement axis or my longitudinal direction is fixed, only then.
Sir,
Okay,
I can
this is
probably
very
define R
crucial.
of t as the position of a particular phase along the ray path as it's traveling. Like you have a particular phase
Yeah, but
traveling
when you
along
are
the path.
saying, Anirudh, that phase, that also has to depend on with respect to what you are measuring, right?
No, as in our ray is some e to the power I kx minus omega t, right? Something like that.
Huh.
So if I say I'm looking for this particular phase, it's
Hmm.
traveling along the path of the ray, right?
Hmm.
So if I'm tracking that particular phase, I can say that is defined by R of t, like a particular trough or crest.
Okay.
I can track
Okay.
that.
It's becoming a bit forced. Yeah, maybe. But then that, I mean, see, why is that really crucial? That is what we have to realize
Yeah, I
actually.
think right now we can move forward. I have
You
some
just move forward. You can
objection. We
go
can
ahead.
move.
So
Yeah.
basically, see, what we need to understand is as long as we are measuring with respect to, see, that phase also you are saying with respect to some point, right? When you're saying later times, Sam's crest, you have to have a reference point. With that reference point, you are going to measure how the phase evolves, right? So here also, I'm saying that we have a axis with respect to which we have first measured the transverse displacement, and then if the transverse displacement is reducing as the ray propagates without invoking time, but then of course if I say the ray propagates, it is obviously going in some time, the time is later time. That is okay. That is why I dared to write this. Okay, I'm basically saying that if the transverse displacement is reducing, then I'm saying that the r dash is negative. If it is increasing, I say that it is positive, and that consistently describes different types of optics that we encounter. That is, I think, only what we are saying. However, what I want you guys to check is very important. That suppose you have, say, if you have multiple optical elements, right? So suppose some little exercise that I will just ask you to do is that you have a ray traveling along a straight path D, and it is then and then, no, not it is, wait, and then focused by lens of focal length, say f. Okay, so then so basically what you have to verify is how you will take. So you understand, right? So there are two ways you can do this, right? You have rf dash, sorry, yeah, it is correct. So if I say this, I can either do this, if I write this as, and this is of course my ri dash m1, sorry, this is m2. I can either do m1, m2 on your this ri dash, or m2, m1, right? So yeah, is it commutative or not? Okay, and it's very simple, but let's start the discussion from there tomorrow. Okay, you understand what I'm saying? Can I arbitrarily change these orders? When I write these matrices down, can I just blindly start operating them from the left, first, second, third, like that? That is crucial, right? Obviously, you can understand that is crucial, right? So you will easily find out that if you interchange these, then yeah, whether it's commutative or not. Okay, so this is this is the basics of this whole treatment. Yeah, so just convince yourselves that indeed it will not be commutative, and what we shall do afterward. Tomorrow is Thursday rather. Very importantly, we will actually look at this thing of resonator stability. That's very nice. So there again, there is something that we will kind of assume something called Sylvester Theorem and all. But yeah, so remember the challenge of doing a resonator is that you will have the ray going in times, right? Infinite number of times forward and backward. So how do we understand that? You understand, right? So you have two mirrors, and the ray will keep bouncing back and forth. So you have a ABCD to the power of n, where n is infinitely large. So yeah, we have to basically uh, see how we can get past it. Okay. Okay. So let's stop
Sir,
today. Yeah. Any questions?
yes,
That is,
yeah,
yeah.
yeah,
Tell me.
yeah. Just one question. So, sir, that
Huh.
means this ray matrix does not uniquely describe the optical component, right? For example, the lens and the mirror both had the identical ray matrix.
No, lens and the dude, your concave mirror, not a plane mirror.
Yeah, yeah, yeah. Right,
Concave
right,
mirror,
right.
if you
Yeah,
plane mirror, money it
concave
will
mirror
become,
and
yeah,
convex lens. Yeah, yeah.
exactly. Concave mirror, convex lens are actually very similar, very, very similar. It's only that they are, but then, yeah, so the angles, you have to remember that if, but just by, of course, the optic, you have to know whether it's an optic and it's a, mirror or a lens, you have to know, right? And once you know that, then you can exactly trace the ray because you
No,
know which direction
suppose
is going there, where.
suppose I have a very complicated arrangement of mirrors and stuff, and I
Mm,
find out the ABCD matrix of the whole
mm,
thing just by
mm,
multiplying, as you had shown.
mm,
So then I know what my RI dashed is, and I
mm,
find out my RF and RF dashed,
mm,
but that won't uniquely tell me where the ray is going. So it can go in two directions, right? I mean, it can go
mm.
forward or backward, like just in the.
No, if it goes backward, then your RF dash will change, right? Going forward and backward means the thing will still be a
No,
problem,
sir.
right? In the sense of,
Think about the
yeah.
convex lens and concave mirror case. Like
Mm,
there,
mm.
the like
No, but
if I
there it's impossible. So there it's sorry, there it's important to note that if you know that it's a mirror, then
yeah,
the thing either will be this way or it'll hit and go the that way, right? So
yeah,
that you
yeah,
know, where it's a lens, you know it's this way. So
right,
you
right. But
always,
yeah,
blindly taking this will not help.
right, right, right.
Okay, you have to remember what optic is there. Yeah,
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 so
that
that
is
was
true.
my point when I was
What
saying.
optic you are putting, that you have to know.
Yeah, so
Okay,
that was what I
okay.
meant to whenever like doing the algebra, if you get a final answer
Hmm.
of r and r dash, you can't tell from
Ah,
that vector
maybe
key what your ray is going
optic
to
as
look
well.
like. You
That
have
I
to know
agree.
the
That I
component
agree
key.
because,
uh,
huh.
like that's
No,
what
but
they
at the same time,
continuously
Anirudh, if you
uh,
give the, for
say.
example, if you give the convex, concave mirror radius of curvature, you know how it is, right? So that units are also will be different, right? The focal length will be something, radius of curvature here. At the same time, you need to know what the optic is because that is expected also, right? Because you are given all the optics and you assimilate them and you find out how the rays are. It's not that, the problem always works that way.
Yeah, but the thing is, I think there can be a formalism where you can make it unique in such a way that you can just blindly apply M1, M2, M3, M4, and you get the final answer, and
I
you
understand
get the
what you're
vector
saying.
directly. Ki this is the ray. I mean, theoretically,
That
there is
may be
nothing.
there. It's not typically, yeah, it's not I don't know of this. If you are going to, yeah, put a time thing as well, and then, yeah, uh,
Sir, you need not put a
not
time
time, and then
thing.
some,
So you need three parameters.
hmm.
Like
But
the
in
way I
which
see it,
direction it is
you
going, you
need.
have to probably trace because this one doesn't tell you. These are basically scalars. RF and RF dash are all scalars. There is no vector treatment. It doesn't tell you which way these are. If you're, yeah, that is.
So I think you can just give a simple treatment in the way you can say Z and uh, K, so some KX and KY or something like that. Like
Hmm.
uh, in the two perpendicular directions, what is the K
What
vector
is the thing?
basically?
Maybe.
And
But see, I'll see the most important thing that we use this for is actually to find out resonator stability because that is the main thing that you do. Okay. And there you don't need this. There are totally different approach for that. But of course, if you are designing, say, a for example, a car, as I said, a mirror, a headlight or something. There, of course, that is important. But there again, because you know all the individual components and how they are going to interact with light, typically, because see, in a software and all, you take the optic and you place it somewhere, on your picture, you place it and then you just allow it to run, and then the thing knows what you are putting, right? So it is not that you're
So the
giving a black
software
box
won't.
and it finds you.
So if you just provide the software with the matrix and the R and R dash,
Yeah.
it won't know where the final
No,
ray is
but it
going.
knows, right?
That
Because
information we'll
the
have to provide.
moment, yeah, when you know that it's a mirror, it knows that how the ray goes, right? That is built inside. When you
Acha,
know
okay,
that it's
yeah.
a mirror, it will know that ये जाके ऐसा करता है. But for example, you give that, you have to define that element. If you just give the matrix, it's not enough. You have to define the element and then give the matrix and the parameters. Then it knows that how it will go. Okay, so it knows that if you put a mirror and then you apply this, then the ray will not go through it. It will bounce back. Okay, that part is built into the code. That they typically give. But I am not aware of some general, yeah, that k vector thing, as you said, may be done, but I don't think they have done it actually. It is there because typically when you give a mirror or a lens, you say that it's a mirror or a lens, and then it knows that a mirror will reflect, a lens will transmit. That is clear. Okay. But yeah, you can actually find out if you guys are interested. Just do a search on Zemax. Zemax might have a free version. It's a very useful tool, very useful tool for designing telescopes and all that. Is very, very useful. They might have a free version, but it's obviously will be very limited. But yeah, so industrially, these are very, very commonly used. If you want to design cavities and all, cavity designing, so of course I'll tell you there's a different way. Again, cavities, cavity, the stability is what is crucial actually. If you just know that whether a cavity is stable or unstable, then we essentially couple this with Gaussian optics. Okay, so Gaussian optics, that tells you different stuff. It tells you how the Gaussian waste, as is the Gaussian beam spot, how that evolves. Okay, so that's a bit of a different thing. We will incorporate that, and that gives a roundness to this actually. But the resonator stability, as you see, we'll do tomorrow. That's actually nice, actually. So yeah, let us go forward for that. In the meantime, you can think if you find something that is interesting. I don't know whether people are. I mean, yeah, I'm not really familiar with if any this vectorial thing is there. Might be interesting. Again, this is a topic that one might look at if you're interested, really.
Yeah, I mean,
Okay,
if you're considering 3 dimensions, it would be
it
this
would be
would
interesting. I agree. I
yeah.
agree. I agree. But you can look at it. So if you find it something, please tell me. Okay.
And
So let's
there
stop.
the they're saying negative and all.
It
That
doesn't
would be a
matter
bit
then.
complicated.
It will
Like
be, yeah.
saying that this direction would be negative. 3 dimensions may it will I think be a bit complicated.
Typically, we don't care so much because okay, okay, yeah, okay, okay. So
There,
there,
I think the just
ah,
K
ah,
vector
ah. Mm,
convention would be better. Like you know
mm,
where which direction exactly the ray is propagating in.
that might be.
Here we are here we are
Mm,
like the two parameters just tell you the line along which the ray is
that's correct.
and the
If you
direction is
have a
pretty
bending
clear.
or something, if you have a bending, so basically it just tells you where yeah, I mean, in the sense that uh, depending on where finally, if you really look at it, I mean, image formation and all also might be a bit complicated. I think the biggest advantage of using these is for cavity resonator treatment. Okay, instead this is really not telling you where an image is formed. That if you really think of it, tells you where a particular ray starts. So if you want to find out images, then you have to define each point of the image. You have to define a ray, and then you have to see where all the rays converge and all that, and then you have to basically form the image. So that is very non-trivial using this. The biggest use of this is in designing cavities. That is what you will find out. You understand, right? When you want to form an image, it's very non-trivial using this, because image money, you have to take every point as rays, and then each of them has a different art dash and this thing. then you have to see where they all meet and then construct. Softwares do that. Softwares do that very well. You understand? So softwares, they will just take the image and then they will. So that I think they keep track. So that I actually don't know, I mean, how they keep any change in. For example, if you have a perpendicular mirror, then the whole axis just shifts by 90 degrees. That and all. That how they keep
Yeah.
track. But yeah, that is interesting actually. I don't know. I mean I have used them, but they just, those are dumb things, right? You tell them, they will. I mean, everything is inbuilt, so you don't really bother. And industrial research also doesn't care because they just want results. They don't want to know how it's working, mostly. Okay, but that's an interesting point, though. Anyway, chalo, let's stop today. Let's pick it up later on. Bye.
Okay.